work it's a work where we want to propose to you a methodology to build a 3D model, mechanical model, in order to describe the mechanical behavior of metallic material. In this case, is applied to fully ferritic DSI ductile cast iron. There are two main ways to describe mechanical behavior. Sometimes a way is the modelize material at the mesoscale, including the main of mechanical behavior at all scale. But we know that material is observed at the smallest scales, around angstrom, for example, the behavior is much more different. Laws that describe the behavior are different. Another one is to modelize material, modeling each phase present in the material. This is our way. We try to build a model in 3 dimensions. So, this is the aim of this work, and we use for this example commercial traditional software. This is the material investigated. It's a ductile cast iron characterized by presence of ferrite as a matrix and the presence of nodules made on graphite. The nodules was generated by addiction of magnesium in the bath in order to generate the first solids in the made on carbon, and then we have a group of nodules in liquid phase. Then we have another group of nodules in solid phase due to diffusion of carbon from matrix toward nodules. We think we have evidence that the mechanical behavior of external skin of nodules is different to mechanical behavior of core of nodules because of the phenomenon that implies the construction of nodules are very different. The first one we have a presence of diffusion in liquid phase. In the second way we have diffusion in solid phase. It's different. So, this is the phase used to build our model. It's a simple metallographic preparation of surface, and the difference is the presence of indentation in one point near to nodule. This is important in order to check the same position for different metallographic slides that we take with light optical microscope. We proceed in this way. Make a metallographic photo on the surface, then we grade the surface about 3 microns. We prepare another one, the surface, metallographic preparation, and take another photo, and so on. In this case, we have a presence of different layers of material, and we can rebuild the 3D model in this local position. Each surface, each photon was processed by using this formula. Take the probability of presence of different colors. For us, the color is an index of chemical composition, graphite or metallic metals. Black is the main color of graphite, white of metals. Then we check the variances in order to find the zone where we have a presence of much more black or much more white. To define the presence of metal or carbon, and so on. Classify the class level in different variants, and finally we check the total variance, that is the parameter that we use to find a sort of threshold where we can define the presence of metal or presence of graphite. It's an automatic process to describe a threshold. This is the results of 3 different slides taken in the optical microscope, 1, 2, 3. Okay. Then we have the image processing results characterized by a find of threshold, and then we binarized the photos, having a matrix completely white, a graphite completely black. Another step is to find the boundary of nodules for each picture. It is quite easy, because we can take the derivative of this function. This is a 2-dimensional function. X and epsilon are the position, and zeta is the color. 0 if white, or 250 if black. Okay. The region where we have high values of derivative is the boundary of this function. And result is here. We can take the correct boundary of phase, and we have also presence of defect of preparation. We have to eliminate in this evaluation. Then we use a commercial CAD software in order to construct the wired 3D model. This is a region, is a sort of a short box of material, including the main nodules that we want to study, and other presence of other nodules that we want to clean from the. This is a 3D solid shape of real nodules. It's not a very spherical nodules. Then we use typical mechanical properties of matrix and graphite in order to study the simple volume of this material by a commercial FEM software. This is the first result. We check in the literature the presence of a lot of models that treat the presence of nodules as a simple rule. Our first example is a sort of box made in metal matrix with the presence of an hole, but this hole is characterized by the same shape of nodules. Okay? The load applied on the surface is near to real stress. And we can see it's about 400 megapascal. We can see in this slide the presence of an higher values of home stress. It's about 563 megapascal. The second example was to use in the hole the presence of graphite. In the same position, at the same condition, you can see that the maximum value of stress is decreased. It means that cast iron can be modelized by matrix characterized by presence of holes, because in the holes there is a material. The effect works with completely different. So another kind of results is the presence of damage. At the same condition, we can see the presence of a sort of the bonding, but not in the graphite matrix boundary, but it's inside two nodules. We have an evidence of this kind of damage. We named this kind of damage as onion-like damage, and it's investigated and predicted with this kind of modelization. So this is the conclusions, and we think that it's not so easy to reconstruct the 3D model, real 3D model, using simple, complex investigation. But we can automatize all the phase that implies an image processing of results. We can make this kind of analytical computational phases, and the results are much more easy than we had in the past. Thank you very much.